Hello everyone, welcome to our project presentation. I am Dhanapalan and my teammates are Harikrishna and Jai Philbert. We are the final year BE students from the Department of Electrical and Electronic Engineering at the KLN College of Engineering. Our project is carried out under the guidance of Mr.R.Thangasankaran, Assistant Professor of EEE Department. Today we are going to present a project under title Design and Analysis of AC to DC SEPIC converter for the low power application. Our goal was to design a compact and efficiency converter for the application like LED drive that not only convert power but do it cleanly, meeting today's standard in the term of power quality and efficiency.
In modern low-power applications like LED lighting, battery charger, or other embedded systems, a clean and efficient AC to DC conversion is critical. Traditional rectifiers have a major flaw. They introduce a lot of harmonic distortion and operate a poor power factor, which basically means they draw a misleading current from the grid. That's a problem. Our motivation came from the wanting to build a converter that inherently fixes this. Using a SEPIC topology operating in discontinuous conduction mode (DMC), this flows for a natural power factor correction and drastically reduces the total harmonic distortion, helping us comply with IEC 6100032 Class C power quality standard. The system is designed for a 15 watts LED driver with 230 volt AC input and 15 volt DC output at 1 ampere.
The SEPIC or single-ended primary inductor converter is a non-isolated DC to DC converter that can step up or step down voltage with a continuous input current, making it excellent for reducing EMI, that is electromagnetic interface, and harmonics. And the components we have used are inductors, two inductors L1 and L2 for energy storing and transferring, and a coupling capacitor C1 for energy flow between the inductors L1 and L2, and a MOSFET switch controlled by the PWM for a microcontroller, and a diode is used for unidirectional energy flow, and output capacitor is also used for the filtering of the DC output voltage to get it minimum ripple content. And during the on period, the switch L1 is and switch is on, L1 gets charged, C1 discharges through L2, and in the off time of the period, the stored energy is released via the L2 to the load. This can be explained in the MATLAB and also in the hardware components.
We designed the converter for 20 kHz switching frequency, a balanced trade-off between switching loss and size for passive components. Our calculated values are duty cycle is equal to 4%, inductor and L1 and L2 is equal to 0.777 millihenry, coupling capacitor C1 is equal to 0.68 microfarad, and output capacitor C2 is equal to 333 microfarad. Input current ripple less than 2% and output voltage ripple less than 1%. These values were selected to ensure low ripple and minimal switches.
Let me explain the MATLAB simulation for our proposed AC to DC SEPIC converter. Here the AC to DC conversion is achieved using a diode bridge rectifier, and a filter capacitor is placed across the input of the SEPIC converter to ensure low ripple content in the DC voltage. The DC to DC conversion is performed using the SEPIC converter topology, and the MOSFET gate pulse is generated using a PWM generator with a PI controller for closed loop operation system, ensuring highly stable operation of the converter. Here we can observe the MOSFET gate pulse, where the on time of the MOSFET is very low due to the 4% duty cycle for buck operation. During the on time, the inductor L1 gets charged and L2 gets discharged. During the off time, the coupling capacitor C1 gets charged from the energy stored in the inductor L1, and this operation continues. This is the output voltage waveform with the minimum ripple content of 15 volt DC. This is the output current waveform with the minimum ripple content of 1 amps DC. This is the input voltage waveform which has minimum ripple resulting in a very low THD percentage.
Okay, let me explain the hardware components. In hardware components, we have two sections, that is AC to DC and DC to DC. The AC to DC is converted by this bridge rectifiers, and these diodes are used for that conversion, and these capacitors are used for the filtering of the ripple content in the input voltage sources. And the second section, DC to DC, is given by this SEPIC converter topologies. In that we have two inductors, one is L1 and L2. This L1 gets charged when this MOSFET is on, and this L2 gets discharged, and this discharging voltage is given to the capacitors C2, and this capacitor is connected across the load side. And here is a working demo print that we have designed it for the 15 watts, and the 15 watts lamp glows with 15 volt and 1 amps supply.
Yeah.